Welcome to the beginning of chapter 2. So in chapter 2, we're going to be talking all about relations and functions. So our learning target for today is we want to be able to graph relations and we want to identify which relations are functions. So the overall idea that we're going to be talking about is what is a relation? So a relation we can identify as pairs of input and output values. Now, you've already learned this, actually. Input and output values, we're talking about domain, which are going to be the x coordinates, and range, which are going to be the y coordinates. Now, that language is very important, knowing that the input is the domain, which is the x, and output is the range, which is the y. That is going to be really, really critical throughout this chapter that you understand that, and actually for the rest of Algebra 2. Now, there's four main ways that we can represent relations. We can represent them as ordered pairs, as what's called a mapping diagram, as a table of values, or we can plot those ordered pairs as a graph. So those are going to be the main ways that we investigate this idea of relations throughout this section. All right, so let's take a look at another example. When skydivers jump out of an airplane, they experience free fall. At 0 seconds, a skydiver is 10,000 feet above the ground. At 4 seconds, he is at 9,744 feet. At 8 seconds, he's at 8,976 feet. And 12 seconds, he's at 7,696 feet. And at 16 seconds, he is at 5,904 feet. So what I've done is I've set these up for you in those different ways. I've created a mapping from the input to the output. The input in this case is the time he's been free falling. The output is his height. Put it as ordered pairs. And you can tell the input, we've taken the input as the x values, output as the y values, and created those ordered pairs. A table of values. And again, table of values still uses this idea of x and y. And then graphically, obviously you know the horizontal axis is x, vertical axis is y. So again, all of this is stuff that you've seen before, just maybe not named in these particular ways. So what we want to do, what are the domain and range of this relation? So the domain. Again, domain, think those x values. So the x values that we're using, we have x values of 0, 4, 8, 12, and 16. So that's all of the domain, the x or the input. The range or the y values. There we have values starting at 10,000. And I'm sorry, this is going to be a little bit shaky. 10,000, 9,744, 8,976, 7,696, and 5,904. So when you're dealing with distinctive values, with points or particular inputs and outputs, all you have to do for domain, list the x's. For the range, list the y's. Now, there is another way of determining domain and range, because often throughout the rest of this course, we're going to be talking about continuous graphs. So graphs of lines, parabolas, absolute values, all those kind of things have graphs. So in the future, that's typically what we're talking about. So as a hint for this, you want to look to see if there's a minimum or maximum value that x or y values can have, and then write an inequality statement in the appropriate direction. Or if x and y just continue off in both directions, either one of them shows that they can take on any value, then you can write all real numbers. So let's take a look at what I mean by that. So looking at this first graph, the first graph is most definitely a line, which you are very familiar with. So for the x values, okay, notice you can see it's kind of taking on all x values. It's going off the graph and off the graph. So it's taking on any possible x value. So because of that, because it can take on any x value, there's no minimum or maximum that it can be, we're going to say the domain is all real numbers. All right? For the range, again, notice it's going off the graph downward and off the graph upward. So again, there's no minimum or maximum. There's no limit to what values we can choose. We can get any y value out of that function. So once again, we're going to be getting all real numbers. So for lines, that's real easy because honestly for lines, that's what's always going to happen. All real numbers for both the domain and range. You can use any x and get any y out of it. Now let's talk about the next graph. Now I know you haven't seen that type of graph yet. It's called an absolute value graph, and we'll get back to that later this chapter. But let's talk about the domain and range. So for the domain, again, we're talking about x values. So what I want you to see is if you continue this graph going and going and going, I hope you can see that the domain is continuing. It's going to go forever continuing in the left and forever continuing in the right. As it increases in both directions, it's just going and going and going. So this is another example where you can see as it expands, it's going to encompass all the x values. It's going to encompass all real numbers for the x. Again, recognizing the x is the horizontal direction. Now vertically. Vertically, I want you to notice something. So what I want you to notice is look at this point down here. All right? We're seeing kind of a minimum value. We're seeing the lowest value that it can be. And then there's nothing below it. Notice all of the y values, it's going above. It's going up forever. But there's nothing ever below that value. So this is that case that I was talking about. So we're going to want to represent this with an inequality. So this has a y value of -4, all right? And notice, it can be -4 or anything above it. So that's how we're going to designate the range. The range are y values that we're seeing. Our y values are going to be everything that are above or equal to that -4. So again, I've identified a minimum that it can be, and then I've identified the direction. It's going to be everything greater than that value. Now let's look at the third one, that ellipse, that oval shape. So again, identifying domain and range. All right, so for the domain and range, here I notice horizontally the x values, you can have any x values between there, but it kind of cuts off. The x is never going to get lower than that value there or higher than that value there. It's stuck in between there. And the cool thing is we know how to use an inequality to write that. The x values are stuck in between there, but it can be any value in between there. So we're going to say the x is squished in between -6 and 6. This is the case where it's bounded in both directions. Well, what about the range, the y values? Well, kind of the same thing is happening here. I see a lowest and a highest value. It can be anything in there. but it's never going to get higher or lower than those values. We have a little range that it's bound within. So again, we're going to represent that with an inequality. Our y values are all going to be greater than -2, but stuck equal to or less than 2. So again, you can also use inequalities as a bound if they're bound in both directions, such as that. But you're always using domain to track the x or the horizontal direction. You're using the y to track the y's or the vertical direction. So the next step in talking about these relations, we've talked about the domain and range, but the next thing we have to do is we have to talk about what makes a relation a function. Because that's the key thing here, is what relation is going to be considered a function. So a function is a relation where each element in the domain corresponds to only one element in the range or the y. So each input, each x, can only go to exactly one value in the range, one y value. Okay? Now, I want you to be very careful with how you're looking at this. So each x can only go to a single y. Multiple x's can go to a y value. So let me see, or let me explain what that looks like. So here in A, every x is going to only a single y value. There's only one line leaving each x value. So that actually does, in fact, make this a function. You're only tracking the x's, okay? There's only one thing leaving each x. All right, now B is the same thing. There's only one thing leaving each x. So B is also a function. Each x only corresponds to a single y value. Now C has some trouble because the one here, you have two things leaving that x. The x is going to two different values. That is a problem. That is going to make this not a function. X cannot go to two different values. X is going to -7 and is going to -9. That is not okay. So that is not going to be a function because it doesn't follow the rule that each x should only be going to a single y value. All right. So that's what it looks like in mapping, how to tell the difference between a function and not a function. Let's take a look at what it looks like when you're looking at points. So here, when you're looking at points, you want to look at each x and make sure it's only corresponding to one value. All right, now here we have a problem. And the x value of 4 is going to -1 and it's going to +1. So that x value is going to multiple y values. So once again, that is not going to be a function. You have an x going to different y's. Let's look at these x values. All of those x values are distinct. Each x only is represented once, which means each one is only going to a single y value. So in E, that is a function. Okay, each x is represented one time and is going to its y value. So that is completely acceptable, and that is going to be a function. What about F? Well, in F, I want you to notice these two values right here. Okay? -2, 1 and -2, -1. So if you notice, when they're stacked on top of each other like that, notice the x value. That x value is going to two different y values. Okay, so that graph right there, that is not going to be a function. Those stacked points have the same x going to different y values. So that is not going to be a function. And that actually leads into one of our rules that we're going to discuss on the next page. So when you're looking at something graphically, we have what's called the vertical line test, all right? And the vertical line test is a way to see if points are stacked like that. Because if they're stacked, it doesn't work. All right, it's not going to be a function. So what the vertical line test says is if you can put a vertical line anywhere on the graph and it touches in more than one point, it fails and it's not going to be a function. So for example, this circle here, I can make a vertical line and it touches in multiple points. So because it touches in multiple points, that is not going to be a function. All right, so that's what the vertical line test says. Again, if you can make a vertical line and it touches in more than one spot anywhere on the graph, it is not a function. So let's look at a couple of things that are functions. Look at B. If I make vertical lines through those points, notice they only touch each point once. There's no vertical line there that touches in more than one place. So this is an example of how the vertical line test can pass. Okay, it's saying that this is a function because every line that you make only touches in one place. And again, that is what makes it a function. If it touches more than once, it fails. C is another example of a function because notice, anywhere I put a vertical line, it's only ever touching the function once at a time. All right? And again, because of that feature, because it's only touching in one place, that is making this a function. And again, that is the easiest way graphically to determine if any relation is a function. It's just drawing those vertical lines, convincing yourself either, yes, I can find a place that touches twice, making it not a function, or no, there's nowhere that it touches twice, therefore I don't have to worry about it. All right, the last thing I want to cover is talking about function rules. All right, so function rules is an equation that represents an output value in terms of an input value. So essentially, it's an equation. All right, and you've seen equations a lot. For example, linear equations, where the y, again, as the output, is the dependent variable, and x as the input is the independent variable. You're choosing x's and you're producing what y value corresponds to it. Now this leads to what we call function notation. So function notation, we're used to thinking things as y equals 3x plus 2, y equals negative 2x minus 5. Now function notation is saying that you can say f of x, the function of x. And that's exactly the same thing as putting a y there. All right, so again, let me just reemphasize. Function notation, what it says is that f of x you can use, and it means exactly the same thing as y. And in fact, on the next slide, I'm going to show you why it's actually beneficial to use that. So here is asking us to find the outputs for each of the following. Now, the cool thing is, it's a lot less wordy this way. If I give you a function in terms of f of x, so f of x is x squared plus 5x minus 3. That's my function rule. If I'm asking you for f of 2, what that's saying is that 2 right there, I'm putting in my function everywhere that there was an x. All right, and again, as I substitute those values, I'm sorry, that should be a 2. And as I substitute it in, I'm putting parentheses everywhere. But all it means is you're substituting 2 in for x. So evaluating that function for 2. And again, 2 squared, you'll get 4. 5 times 2, you'll get 10 minus 3. 14 minus 3 leaves you 11. So f of 2 equals 11. Or another way to say that is 1 point on this graph when x is 2, y is 11. So again, this notation, it actually makes things a little bit cleaner than they were before. Because now we can just say, hey, find me f of 2, and you know to just plug 2 in. Or the next one, f of negative 3, means I'm putting negative 3 in everywhere that x was. All right, you're just substituting in that negative 3 wherever x was. So you're getting 9 minus 15 minus 3. So 9 minus 18, you're getting a negative 9. All right, or again, that means that a point on that graph corresponds with having an x value of negative 3 and a y value of negative 9. Or you could also use an absolute value equation. So here, substitute h for negative 7. So h of negative 7 means, again, I'm putting in negative 7 wherever the x was in that equation. Negative 7 plus 1 is negative 6, but the absolute value makes it positive. So 6 minus 5 leaves you with 1. So that's telling you a point on that graph for an x of negative 7, it has a y value of 1. All right, so we're almost done. Just one last thing. So when trying to write a function rule for a real-world problem, determine which variable is dependent and which is independent. So a pizza costs $14 with a flat delivery fee of $1.50. Well, function rule models the total cost of the number of pizzas delivered. So I'm going to let P represent my number of pizzas. C is going to be my cost. All right. So my cost of this, well, for each pizza, I have to spend $14. So each pizza I'm getting is $14. And then there's a delivery fee of $1.50 that I have to attach on at the end. A flat fee that has nothing to do with the number of pizzas that I'm buying. So they want us to evaluate that for getting 5 pizzas. All I do is I plug in 5 to that formula. I evaluate it, and those 5 pizzas would cost $71.50. And that would be the end of my problem. That would be the cost of getting those 5 pizzas. All right, so lots of good stuff in this video. Now, don't forget, I need you writing those summaries. I want you to summarize what I've told you. And again, in this one, there's a lot of wordy stuff, a lot of really good stuff. So take a moment and write that summary. Summarize what you learned, the big ideas from this video. And then come back ready to do the practice work in class.